Okay, so while our speaker gets ready, let's introduce him. So the next speaker is Hongzheng Chen. He's a fourth-year PhD candidate at Cornell University under the professor Zhang. His main task focuses on compilers and accelerator architecture for large-scale heterogeneous computing, especially optimizing machine learning workloads. He's author of 10 papers, more than 10 papers, which is a great result for a fourth-year PhD, and is also been the candidate for best paper, various best paper nomination, and is also the winner of some of these nominations. So the expectations are quite high, and is also been named as the machine learning and system rising star of 2024.
Maybe that's fine.
Great. Floor is yours.
Okay, thanks for the introduction. And I'm Hongzheng from Cornell University. And today I'm going to talk about a Python embedded programming model for composable hardware accelerator design. And today's talk is quite different from the previous talk. So basically, we will focus more on the high-level programming model. Okay. Okay, so nowadays, as more and more applications are developed, so we are facing growing imbalance between software demand and hardware support. Millions of software developers build applications for machine learning, data analysis, and scientific computing in different domains. And many of them require specialized hardware to accelerate. But only a small number of hardware engineers are responsible for designing accelerator for them. So this imbalance places a heavy burden on hardware engineers. The reason for this lies in the complexity of specialized accelerator design. To clarify, I mean hardware accelerator in my talk here instead of the particle accelerators that are used in CERN. So actually designing a specialized accelerator is quite different from programming on general processors like CPU and GPU. It requires manually handling the custom keys, custom memory hierarchy, and custom data communication, which is far more complicated than general programming. So the first challenge in designing high-performance accelerator is to strike the balance between manual control and compiler optimization. And one common approach for accelerated design is leveraging C++ high-level synthesis. So here I show an example of a matrix multiplication kernel written in HS. And we can see that even with the help of HS, the code is still very complicated. So to optimize the performance, we must firstly apply compute customizations such as loop tiling, unrolling, and pipelining, which requires manually rewriting the loops. Furthermore, we also need to include custom memory hierarchy by creating intermediate buffers and conducting memory partitioning. So lots of pragmas will be inserted. Lastly, we also need to incorporate data movement optimizations. It requires programmers to restructure the code into multiple pipeline stages and then connect them using FIFOs. Actually, this example needs about 500 lines of HS code, even for a small 6-solid array. This approach is vendor-specific and not able to be reused across different applications. So to address these challenges, we propose Allo, a Python embedded accelerated design language and compiler. The name Allo is derived from Allosaurus, meaning support for different hardware architectures. That's why we have a dinosaur as the logo. An Allo Python program is firstly processed by a parser and type system for basic checks before being lowered into the MLR ecosystem. And the optimizations are performed at the IR level. Given the strict correctness requirements of the hardware design, we also incorporate a verifier to ensure the transformations are correct. And on the back end, Allo supports multiple target devices, including CPU for simulation, FPGA and ASICs for accelerated design, and AIE for edge acceleration. And we are also building an open source HS backend that lowers the ML code to keyless and the circuit project. And for the front end, we have a PyTorch interface that can directly import PyTorch models and generate efficient accelerators. So to support large-scale applications, it's very crucial to adopt a bottom-up approach with modular design. So Allo supports this by allowing users to provide behavioral description, which specifies what the modules compute, and also the structural description, which defines how the modules are interconnected. By specifying both behavioral and structural descriptions, software engineers can easily port their applications as hardware modules, and hardware engineers can efficiently compose these modules into a larger system. Now let's look at how an Allo program looks like. We follow several principles when designing our front-end language. The first one is Pythonic. Since nowadays, Python is the most commonly used language in machine learning and data analysis, so a Python embedded language is more acceptable. As shown on the right, users can directly write an Allo kernel in Python using a basic 3-level nested for loop to calculate C equals to A times B. And we support freeform imperative programming and support Python native keywords, so users do not need to learn a new DSL, but can easily write a Python program as usual. The only requirement is that we need to explicitly annotate the types, which Allo will use this to infer the bit width of the resulting hardware modules. Due to this flexibility, Allo can easily express different applications, including those algorithms widely used in CERN, like track finding, classifications, and clustering. And we also think it's very important to reason about the hardware optimizations at a higher level. So we employ the idea of separations of concerns and provide a schedule language. Allo does not only decouple the compute customizations, but also decouple the memory and communication customizations from the algorithm, which enables more complicated optimizations. And in the middle end, we use MLR as the intermediate representation. Allo enables spreadwise verifiable rewrites. So users can print out the transform module, and after applying each primitive to inspect whether the customizations is expected. And in the following, I will use an example of transforming matrix multiply kernel to a 6-solid array to demonstrate how to write a program in Allo. So after users define an algorithm in our front-end language, we can create a schedule by calling allo.customize. A schedule here is a sequence of customization primitives. And we can see from the architectural diagram on the right, the default implementation only has one PE and reads the data from A and B tensors, and then write back to C. After creating the initial schedule, users can apply schedule primitives to customize the hardware design. For example, here buffer add is to create intermediate buffers between the PEs and the input arrays. Partition is the memory customizations that create more memory banks along specific dimensions. And .2 is the communication customization that connects the buffers with PEs using FIFO. And using these primitives, we can generate this output stationary 6-solid array with only 8 lines of schedule code, which greatly simplifies the programming burden to construct a complicated data flow architecture. And then to test whether the results are correct, we can lower the code to the CPU backend. Users can directly pass in the NumPy arrays and leverage the LLVM execution engine to run the optimized module. And apart from the basic CPU simulation, we also provide a stronger correctness guarantee for our customizations, especially for those data flow programs that cannot be easily simulated on CPU. So we integrate a formal equivalent checker that we propose in the FPGA 24 paper to formally verify the equivalence of the transform module and the vanilla module. This verifier uses symbolic execution and can currently support statically interpretable control flow and verify large designs very quickly. And after we make sure the design is correct, we can just change the target to Vitis flow to generate the bit string and deploy it on an actual FPGA. And still, users can use the NumPy interface and pass in those tensors into our module to directly execute the hardware. So this end-to-end process greatly simplifies the process of simulation and deployment in a push-button way. Now, suppose we have already optimized the individual kernels. With the next questions becomes how to compose these kernels into a functionally correct and high-performance accelerator. As I mentioned earlier, there are many ways to compose kernels in Allo. In this example, I show a common pattern from a transformer model that is cascading two match multiply kernels by function calls. Since different function arguments may require different layouts, we need to ensure the consistency of the function interface and the actual variables passing into the function. So for example, the y here used as the output of the first kernel and the input of the second kernel needs to be consistent. Otherwise, if the interface mismatch, then the kernels cannot be connected together. And to make sure the interface is consistent, we can create a use-step graph for the function arguments. And the key idea here is that we can model the data layout such as the memory partitioning as types. Basically, partitioning on hardware means creating multiple banks. So we introduce 4 base types to describe the partition strategies: complete, cyclic, block, and no partition, which are very similar to the HS partition pragmas. And then we can construct a subtyping relation between these base types. We want to make sure we always provide more and read or write parallelism for the variables so the kernels can always execute correctly. In this way, the data layout compatibility problem just becomes a type inference problem in this type system. And more importantly, we find this type system has a very good lattice structure. So this inference algorithm is very efficient and can converge in linear time. And similar idea can be applied to structural composition, where we connect different modules in a dataflow manner. A string can also be viewed as a layout that enforces the memory access order. A string is associated with base type T and 2 operations. The put operation places the data into the string, and the get operation retrieves the data from the string in a first-in, first-out manner. And the code snippet here shows a simple producer-consumer pattern. We wrap the data flow kernels in df.kernel decorator and connect them using a pipe. Basically, the producer kernel only needs to put the data, and the consumer kernel reads the data from the pipe and do the computation. And using this streaming interface, we can actually construct more complicated data flow patterns. Here we show the output stationary six-solid array again. Compared to the previous transformations with primitives, this implementation is more straightforward. Users only need to specify the actual work inside one kernel. For example, the peripheral kernels only need to load the data and then send them to the compute PE. And we can use meta-if and meta-else-if to specify the functionality of a specific PE. And those conditions are evaluated at compile time. So no additional control logic will be generated. Then each PE only needs to read the data from both sides, conduct a dot product, and then pass the input to the neighboring PEs. After writing the computation inside one kernel, users can easily scale the design by specifying the mapping. Since this interface is target independent, we can use it to generate datable architecture or target existing datable accelerators like AMD AI engine. And using this streaming interface, we can not only transfer the scalar data, but can also transfer a bulk of data between hardware modules and create ping-pong buffers for them. This actually is very useful for many applications that requires a large amount of data transfers. So this greatly enhances the expressiveness of the interface. So with these two types of composition, we show that we can achieve high performance for a single kernel and multi-kernel design. In this slide, we firstly conduct a single kernel evaluation on the Polybench benchmark, which consists of lots of basic kernels in scientific computation. We compare Allo with other baseline systems, including the basic Vitis HS, 3 accelerator design language as HCL, Dahlia, and Tilog, and also 2 HS compilers. And we can see that Allo can always achieve the best performance in these designs with orders of magnitude better than the baselines. This is mainly because Allo has sophisticated memory and communication customizations that creates efficient memory hierarchy and data placement schemes. And apart from latency, we also conduct analysis on resource usage of those designs. Compared to the state-of-the-art HS compiler scale HS, Allo achieved a lower latency by reducing the II to 1. Since the design is better pipelined, we also achieve a higher pace and route frequency. And to demonstrate the scalability of Allo, we also conduct a multi-kernel evaluation by constructing a complete LLM accelerator. We take the context GPT-2 model and then create a fully pipelined datable architecture for this model. In Allo, since we have already optimized the single kernels, we can directly compose each submodules together to form a complete design. And we mapped the design on an AMD U280 FPGA running at 250 megahertz and evaluate the design in a single batch, low latency generated inference setting. So we dumped the physical layout on the right, and we can see the implemented hardware modules span across 3 SLR regions on the FPGA, which is unachievable by previous framework like HS4ML. So previous framework cannot handle such large designs and cannot target the latest Vitis 4. And compared to the previous overlay design DFS written in Verilog, we can achieve 2.2 speed up in the preview stage. Even comparing to the A100 GPU with a more advanced 7 nanometer process, our accelerator can still achieve a better performance and much higher energy efficiency from long output sequences. And most importantly, we can achieve this performance in Allo with less than 50 lines of schedule code. This is the first instance of leveraging high-level programming language to design high-performance LLM accelerator. And we are currently extending to support latest models and devices. We also map the structurally composed datable program to other backends. Specifically, we target the AMD AI engine, which includes AIE arrays and is actually a 6-solid array-based datable architecture just shown on the right. And we only need to change the build target to AIE, and the front-end program remains the same. And we can achieve orders of magnitude performance improvement for a gem kernel and a whole CNN model. Finally, we also encapsulate those NN operators into a library and integrate Allo as a backend of PyTorch. In this way, users can directly import the PyTorch model using Allo.frontend from PyTorch and generate the optimized accelerator design in a push-button way. Okay, so in conclusion, we propose Allo, a Python-embedded accelerator design language that is able to generate large-scale accelerators in a productive way. And we are also adding more backends to Allo, including our own simulator and an open source HS backend, as I mentioned in the beginning. And our framework has been widely used by universities and industry partners to build different accelerators. And we are also open to any collaborations. And our code is also open source on GitHub. Please feel free to try it out. Thanks for your attention, and I'm happy to take any questions.
Thank you. Very nice talk. Are there any questions? I don't see. Oh, I have raised hand over there. Calliope.
Hi. Very interesting presentation. But I have to say that most of the metrics you presented here are from a software engineer perspective. What I would be interested in seeing is the hardware engineer perspective. For instance, you have a comparative study of the accelerator of this of Allo based on other accelerators and high-level synthesis tools. But how about all the resources? I mean, using these different tools, you get different acceleration, okay, normal. But how about logic elements, the cost in area? Always, okay, writing pure RTL is always going to be optimized, but how do these compare between one another? I want to see the hardware. What is your cost on area and resources?
Yeah, so actually we also show this comparison here, and also in our paper, there are some details comparison with this Allo-generated accelerator and also compared to other RTL-based accelerators. So actually, we can see that Allo not only achieve better performance, but for the resource usage, they are still better than the RTL baselines. And so using this example, we want to show that even leveraging a high-level programming language, we can still achieve a very high performance in a resource-constrained hardware.
Okay.
Yeah.
I see another question here.
On exactly this page, but you are comparing against 4-bit and 8-bit quantization against FP16.
Yeah, so actually we also have other comparison with low bit width quantization with other baselines. And this is just one example that the RTL design use FP16 as an example.
Okay, and in your previous page, I didn't remember which one, but when you assert that the result from the matmul of the Allo composed kernel is the same as the Python kernel, you had an assert with an error margin of 1 to the minus 3, which is pretty big for FP32 multiplication. So in your composed kernel, is it still IEEE compatible FP32 definition, or is reduced somehow?
Yeah, so we need to make sure the composed kernel or the single kernel accuracy still remains the same compared to the original one. So that's why we have the CPU simulator and also the verifier, just to make sure.
But I'm asking that when you verify it, the error margin was set to 1 to the minus 3, which is a pretty big error margin for FP32. And is there any precision degradation inside, or you are doing IEEE compatible operation under the hood all the time?
Oh, yes. So for matrix multiply, we directly use the DSP48 IP from Xilinx. And then I think the previous example of the gem kernel is just a demo. So basically, we can use a higher precision for those matrix multiply.
Okay, thanks.
Okay, thank you. I was wondering, so I see you cite a paper here. I was wondering whether in this paper there are more example of comparison, maybe also with like other boards, because of course in this comparison, okay, your performance of course is better than other tools, but maybe it will also be hardware dependent, right? So I was wondering whether you have some references where we could find some other comparisons.
Yeah, sure. So basically, I think most of the experiments and also comparisons are included in our FPGA and FCCM papers. So if you are interested, you can refer to those papers for more details.
Okay, cool. I see a question there.
Yeah.
Thanks for the very nice talk. I have a question regarding what if, so you say that your timing performance is much better than some of the other high-level languages. But my question is, if let's say like I use your framework, what if I don't need timing? Do you have enough flexibility for me to try to optimize the timing or resource placement, similar to what we would do in HDL?
You mean many optimizers for the timing?
Yes, exactly. I'm just wondering if there is also like flexibilities for us to also try ourselves to optimize the placement routing, the timing using your framework.
Yeah, I think this is a very good question. So that's why we want to extend our backends to support more other open source or commercial tools. So actually there are some recent work from our groups that is called RapidString and Tapa, and they are mainly focused on optimize the timing and also the placement and routing for the FPGA design. And so in the future, we may target our generated design to this backend, so that we can have a better timing analysis and also potentially provide an interface for users to explore those optimization opportunities.
Thank you.
And are there other questions? Okay, so continuing on this, so basically, if I understand correctly, you abstracted part of the, let's say, compiler instruction and pragmas and so on, and you basically have now a dependency on the tool. You just say, okay, I want to target VTIS or I want to target whatever you want. But don't you lose some control, fine control on what your code will do? For example, if I want to say, do these on these very 4, can I still do it?
Yeah, so I think our compiler is mainly designed for some specific scientific applications. So if you really need some fine-grained control, for example, designing CPU processors, then probably Allo cannot help. So I think this is also the problem of high-level synthesis. So basically, it raised the abstraction level to a higher level, but yeah, indeed, we'll lose some expressiveness, especially for those fine-grained control for the low-level hardware.
Okay, thanks. I did expect that. Of course, it is easier to use, but yeah, there's. Okay, cool. Are there any other questions, either in the room or remotely? No, everyone wants coffee. Sorry. Okay, so thanks again, and let's coffee.
Thank you.